All right. Go ahead and take a moment to copy that, and then we're going to try these problems. Okay, so I see a question from Tasso about explain again with the MgSO4 and the charges. So if we have sodium and chloride and we have Mg2 plus and we have SO4 2 minus, we could think of that magnesium sulfate being much more attracted to each other than the sodium and chloride because they have the greater charge. So if they get the opportunity to get back together, they are much more likely to get back together. And that's why we see a lower I value for it. The I is a measure of how many will break up. So if they have a higher charge, they're more likely to get back together. And that's why the I value would be smaller for the magnesium sulfate than the sodium chloride. Is that what you're meaning, Tasso? Okay, did that help a little bit, or did you want to talk more about that? Okay, just let me know if you want to go over it more during the lab period. We can talk for hours about the Van 't Hoff factor if you'd like. Okay. Would anybody like some more time to copy down the problem? All right, so let's go ahead and start, and I'm going to start with part A. And so part A is the change in temperature equals K times molality. And I'm going to put in the B's here. Now it is up to you whether you want to put this I right here or not. I tend not to do it, and then I just remember that if it's an ionic compound, I need to multiply by the number of ions. Some people prefer to think of this formula as having an I, and if it's not ionic, they just put a 1 in there. So it's up to you which way you want to do it. Like I said, I have a tendency to just do it without the I, but if you want that I, please feel free to put that in. So change in boiling, and now we need K for water because it's an aqueous solution. So here's our water. We're doing boiling, 0.51. And we're doing the ideal solution of 0.100 molal. And in an ideal perfect world, magnesium sulfate should break up into 2 ions. So just to take a look at that, we should have MgSO4 breaking up into magnesium and sulfate. Oops, yeah. All right, so now I'm going to do 0.51 times 0.1 times 2. And our change in boiling point here, I'm going to call this 0.10 degrees Celsius. For the actual boiling, since it's water, it starts at 100. I'm adding in that 0.1, and we get 100.10 degrees Celsius. This right here is in an ideal solution. So this is very similar to what we did in the past. Any questions on this one for the ideal solution? Okay. So I'm going to go ahead and highlight this is an ideal solution, and therefore it broke up into a perfect 2 ions, these 2 ions right here. Now what I want to do is look at the real situation. So we're still going to start with the change in boiling equals Kb times the molality. I'm still going to fill in here and say Kb 0.51 degrees Celsius per molal. Still going to have the same starting molality. All right, but what changes is the ions. So if this is a real solution, this right here is going to change. Now what we're going to do is we're going to look up our MgSO4 for 0.1 molar. Let me get some of this out of our way. All right, so here's our MgSO4, 0.1 molar. And now I'm not going to use 2, I'm going to use 1.21. So if it was an ideal solution, we use 2 because it should break up into 2, but in the real world it doesn't. 1.21, and it looks like Tassa found that value as well. Any questions about why for a real solution we would use this value here instead of this one over here? So 1.21 is the value that I use here. Now let's go ahead and calculate this one more time. 0.51 times 0.1 times 1.21 like so. Looks like 0.0, I'm going to call this 62 degrees Celsius. And so our new temperature for boiling, 100 because we're using water, plus 0.062, 100.062 degrees Celsius like so. So it is similar, but not exactly the same. So it's similar enough that for most calculations, the ideal is just fine, but if you need to know very detailed, depending on what experiment you're doing, then you might have to go over to a real solution. So any questions on what we did here and why the real and the ideal are different and how they're different? All right, so next up is going to be vapor pressure reduction. So we talked about this picture before, and we said that if we have just a solvent all by itself, just like water, there's a certain amount that will be up here in the gas phase. But then we said that once we've added some of these solute particles, and the red are the solute particles, it is harder for the solvent to get up here into the gas phase because it has to get around all those solute particles. So it reestablishes an equilibrium where it has less in the gas phase. So this is why it has a higher boiling point. You've got to crank up that heat to get it into the gas phase, to get it to go around all that solute. But what also happens is that since we have less gas up here in the vapor phase, we have a lower pressure because less gas means lower pressure. So once a solute is added, we have a lower vapor pressure. And this is called vapor pressure reduction. So anytime you add a solute, and it could be ethylene glycol, it could be sugar, it could be salt, you will always reduce the vapor pressure. You are going to create a situation where you have less gas being kicked off. So down at the bottom it says adding a solute decreases the vapor pressure of the solvent, and it is a colligative property, therefore the more solute, the lower the vapor pressure. So any questions on anything here?
What does colligative mean again?
So colligative, going way back to... So officially it means depending on the collection. So if it's a colligative property, it's a property that does not depend on the type of solute. It means we don't care if it's sugar or salt or ethylene glycol or any other solute. All we care is how much we have of that solute. Does that answer the question?
Oh, was that from earlier today?
Yeah, it was. That was our first slide, yeah.
Oh, okay. I'll just watch it
Oh, okay.
later to get more info.
Oh, okay.
Thank you.
And again, if you want to talk during the lab period, we could talk more about what colligative is.
Okay. Thank you.
All right. So any other questions so far? All right, so here is Raoult's law, and Raoult's law has to do with vapor pressure reduction. And the way we're going to use it is we're going to be using it with non-volatile solvents. So there is another way of using this. If you have a volatile solvent, basically you're going to calculate it twice, add it together. We're just going to focus on the non-volatile though, meaning that you've got a solvent that it does not have its own vapor pressure. It's not going into the gas phase itself. All right, so here it says XA is the mole fraction of compound A, and P in this little guy right here is called a naught. It refers to standard conditions. So P naught A is the normal vapor pressure of A at that temperature. So I like to think of this little naught more like an O, and I think of that as our original pressure. So here we're going to have our original pressure. Times the mole fraction. But there's something funky about this mole fraction. Normally we have the smaller number on top. Normally we have solute over everything. But with Raoult's law, and we only see this with Raoult's law, it is the mole fraction of solvent. So you may get a large number, something like 0.9, 0.7, because you have the solvent on top. So that's a common mistake with this one, to put the solute on top, because again, we normally have the smaller quantity on top. This time we're going to need the solvent on the top. So original pressure times the mole fraction of our solvent will give us our new pressure. So the mole fraction is very similar to a percentage, and in fact, when you're dealing with gases, it is the decimal version of your percent. So if you imagine that you are 80% water, you would take the original pressure of your water times that 80%, and that would give you the new pressure. And here we're going to be assuming that we have an ideal solution. So any questions so far about Raoult's law? Okay, so I have a little bit left, and then we're going to go over the lab. But now is probably a good time to take our next break. So let's go ahead and take a 10-minute break, because I am probably going to keep you for about another hour. So let's come back at 7 o'clock. All right, so any other questions on anything so far that we've talked about or that we haven't talked about? Yes, so the second section, I thought they were going to open it wide and everybody could jump in, but they have decided to do it based on the waiting list, so they're going in order. So go ahead and jump onto the waiting list for the section that's open, and then we are transferring people over to the second section in order of the waiting list. I'm going to try really hard to get as many people in as we can. Normally we're restricted to 36 people because the lab for 1B can only hold 36 people. But we won't have that restriction this summer because it's an online class. So I'm going to do my best to get as many people as I could possibly get in there. So just jump onto the waiting list and I will do my best. And I'm supposed to get all the permission numbers by Friday to start help transitioning everybody into one of those two sections. And because they are online sections, it really doesn't matter which one you're in. All right, so other questions? Oh, and I should mention, even though they look like two separate sections, the lecture would be at the same time for them. All right, other questions? All right, so we were just starting to talk about Raoult's law. And so now let's try an example of Raoult's law. So here we have glycerin, and it's a non-volatile, non-electrolyte. So non-volatile means it's not flying off into the vapor phase. Non-electrolyte means it's not breaking up into multiple ions. So it has a density of 1.26 grams per milliliter at 25 degrees Celsius, and the vapor pressure of pure water at 25 degrees Celsius is 23.8 torr, and the density of water, which of course you already know, but it is 1 gram per milliliter. We're going to calculate the vapor pressure at 25 degrees Celsius made by adding 50 milliliters of glycerin to 500 milliliters of water, and we're going to be using Raoult's law right over here. All right, so for Raoult's law, we're going to need our mole fraction, and we're going to need our original pressure or our normal pressure. So here we're given the pressure. This is going to be that original pressure. Now we need to find our mole fraction. So what I mentioned before break is that our mole fraction, which we use capital X for, so our mole fraction is going to be the mole fraction of the solvent. So what that means is it will be moles of solvent over the total moles. And again, that trips people up a lot because we're not used to putting the solvent on top. Okay, so next up, let's figure out which one is our solvent and which one is our solute. So if you had to guess which one is the solute, glycerin or water? Excellent. So I see Andrew saying glycerin. How about the rest of you? Excellent. Excellent. So this is indeed our solute. Any questions about how we figured out glycerin is the solute? So way back when we said whatever we have more of is the solvent, and what we have less of is the solute. So that's how we would know that glycerin is the solute, while water is the solvent. Okay, so let's start off with our water. We know we have 500 milliliters of it. Next, we'll use our density and then our molar mass. Or, yes, density and then molar mass to get it into moles. So 500 milliliters of water. And then for every 1 milliliter, there is 1 gram. And if we were to add up our molar mass, we'd see that there's 18.02 grams of water for every 1 mole of water, like so. So it looks like 500 times 1 divided by 18.02. And it looks like, and we are in 3 sig figs because of our density. I'm going to say 27 point, and I'll say 7.5 for now just to give us a few more digits, but we will go down to 3 sig figs because of density. So don't forget about density when you're looking at significant figures. Density always counts. Okay. Any questions on how I found the moles of water? All right, so next up we need our moles of glycerin. So we have 50.0 milliliters of glycerin. All right, so next up we need our density. And our density is given right over here, 1.26 grams per milliliter. And finally, we're going to need our molar mass. And our molar mass was given right over here, 92.09. And all of this is for glycerin, which I am abbreviating GLY. All right, so I'm going to take 50 multiply 1.26 and divide 92.09, and it looks like 0.68, I'm going to go ahead and say 0.684 moles of glycerin, right, like so. All right, so any questions on how we got our moles of water or our moles of glycerin? All right, so next up we're doing our mole fraction. So we are finding, let me go ahead and copy the whole thing down here. We are finding our moles of solvent, mole fraction of solvent by doing moles of solvent divided by total moles. So our solvent is the water, so 27.75 moles on the top. On the bottom is everything, so 27.75 plus 0.684. So 27.75 divided by 27.75 plus that 0.684, and to 3 sig figs, or actually let me write it out as 4 for now, and we will cut our sig figs down later. Looks like 0.9759, and this is the mole fraction of the solvent. So any questions on how we found the mole fractions of the solvent? So this looks a little weird. Good question. So there are no units because what happened is moles on the top canceled with moles on the bottom. So mole fraction has no units. But good catch. Other questions so far? So I mentioned before that the weird thing here, and we're only going to do this with Raoult's law, is that when we're finding the mole fraction, you have to have the solvent on top. But again, only with Raoult's law, and we only use Raoult's law with our vapor pressure reduction. All right, so now we are just about ready. We're trying to find our new pressure, and that is equal to the mole fraction of our solvent times our original pressure. So mole fraction 0.9759 with no units times our original pressure, way back up here. And there it is, 23.8 torr. Here you can use any unit of pressure. The deal is whatever unit of pressure you put in, you're going to get that same unit out. So we're going to put in 23.8 torr. Now when I calculate these, I'm going to take our mole fraction times 23.8. And here we're going to get 23.2. And again, it's going to be in torr because we had torr for our original pressure. So any questions on how we did our vapor pressure reduction here using Raoult's law? So we're going to move on to osmotic pressure, and this is another colligative property. So osmotic pressure is kind of a weird thing. So the way we think of it is that we can have movement across a semi-permeable membrane, and this is probably something you've seen in biology class. So solvent moves due to osmosis, and it's trying to equalize our concentrations. So in this case, and this is sort of the original chemistry YouTube before there was a YouTube on the internet. Here on the left, we have 0.15 molar. And on the right, we have 0.10 molar. So we should have equal concentrations. That is what the universe is going to flow towards. And right now we have different concentrations. And so we have a movement of solvent and we're going to see this in later slides, but our solvent will flow going to flow from less concentrated to more concentrated. The idea is this 0.10 is too dilute and the 1.15 is too concentrated. So the dilute solution is sharing its solvent with the concentrated solution in an attempt to equalize the water, or to equalize the concentrations, I should say. Now, as that happens, you notice the solution here on the right-hand side starts going down, and it increases on the left-hand side. Now, in theory, it's going to keep flowing across and across until we have almost all of our solution on the left-hand side. But in reality, there's a time when it stops, when it's like, whoa, I cannot handle any more solution. And that time when it stops is when the difference between the levels here is equal to the osmotic pressure. So once a certain amount of pressure builds up on the other side, it pushes down and it stops allowing osmosis to occur. Now, later on, we're going to talk about the idea of a red blood cell. And a red blood cell can take in water. But at a certain point, that red cell could, in theory, stop the water from coming in if it's got too much pressure on the inside. So when we talk about osmotic pressure, we're talking about the pressure that's required to stop that flow of liquid. And you might be thinking, well, hey, why would I want to stop the flow of liquid? Why don't we just let it flow until the two solutions are equal? That way everything's good and everything's roses and rainbows in the world. Everything has an equal concentration. Well, if you're talking about the inside of a cell, it can only hold so much water. If you put too much in there, it's going to burst. So the idea of this pressure is it stops osmosis, in theory, before where the water's flowing into could be damaged. But what we're going to see with our red blood cells is usually the red blood cells aren't good enough at stopping the flow of water, and they do end up getting damaged. But that's the theory behind this osmotic pressure. At some point, we need to stop that flow of water so the other solution or the other container doesn't get damaged. And here is your formula. Pi equals MRT. Now we're near the end of the semester, and I have a lot of sympathy for you guys, especially with the online format now. So I'm going to go ahead and give you this on your next exam. So this will be given. But if it wasn't given, the way I usually remember this is I think of an MRI, like if you were to injure a soft tissue and you need to go get an MRI. So I think of it as an MRI, but it is MRT. And this is capital M. So capital M, we're back to molarity. The pi is representative of osmotic pressure. So I know it's horrible that we use the pi symbol instead of a P. But this little guy right here is our pressure. And it is pressure in ATM. R is going to be our R for ATM. And then temperature, of course, needs to be in Kelvin because we're dealing with an R that involves Kelvin. So any questions on anything here on this slide? Or anybody need more time to write anything down?
And then T stands for temperature?
T does stand for temperature, yes. So T is going to be temperature in Kelvin. Yes.
Okay, thank you.
You're welcome. Any other questions on this one, or anybody needs more time to copy from this one? All right, so it says, what is the osmotic pressure of a red blood cell in pure water at 25 degrees Celsius? And we're going to assume that the red blood cell has a molarity of 0.30 molar. So what we're looking at here is how much pressure needs to be inside of that red blood cell for it to be like, hey, stop the osmosis, I've had enough water, and it is able to stop water from flowing in. So here's our pressure. And it's going to equal our MRT, molarity, times R times T. And again, be careful here. We're back to our standard molarity. So molarity is 0.30 here. R 0.0821. And finally our temperature. So if it's 25 degrees Celsius, what would it be in Kelvin? All right, excellent. 298 or 298.15. Let's go ahead and go with that 298.15. Go ahead and take a moment and calculate out this pressure, and this pressure will come out in ATM. All right, so I'm seeing some 7.3s in there. Excellent. All right, so go ahead and take another minute or so to calculate, and then we'll go over it. Excellent. All right, so it looks like 7.3 is our answer. Any questions on this or anybody getting a different value? All right, so if you had to guess, do you think a little red blood cell with that semi-permeable membrane could handle 7.3 ATMs of pressure inside? Remembering that we're at 1 ATM, right? So Andrew is saying no, and I agree. So a red blood cell could not possibly handle 7.3 ATMs. That's how much it would have to have inside of it to stop the water flow. But it cannot handle that much. So what ends up happening, and what we're going to see in just a little bit, is that when red blood cells are placed in distilled water, those red blood cells end up bursting because they cannot handle that pressure. Okay, any questions so far on our osmotic pressure or how we calculate it?
What should the ATM be for it not to burst?
I would say it couldn't be much more than 1 ATM. So something on the range of like 1.1 or 1.2, but those red blood cells are really flimsy. They cannot handle very much at all.
Okay, thank you.
All right, so other questions?